if there are two pieces of information I can leave you with today, it would be one, don't name your talk in such a way that ends up with sentences like, and the talk will be on, I wrote a language. Two, if you ever do anything cool or interesting, don't tell ATC, they'll make you do an escape presentation. So I'm going to just chat about probably one of the wilder requirements I've had in my life. So we had to write a language for an Excel-like business solution. It's going to be used by data scientists that we're going to use formula to map these measures that was going to output and be used throughout the bank, create these data structures. I'm going to be chatting about why, what led me there. There's a Lexer, Parser, some constructs, type, context, Unrolling, execution, and if there's time, some other stuff. But first, talk about something very important to me, me. I'm a developer at BBD, which is probably evident. I'm a .NET developer. I've been working in the .NET stack for, at the end of this year, it'll be 5 years. From like Windows Forms, Windows Services, web services, to even making a mess of Xamarin. I've been working at BBD since last year, June, and yeah, it's been great. My mom says I'm okay. So why? Why do we end up here? How do we end up here? What is this? So, first of all, the environment. It's .NET, pretty much through the very much Microsoft stack. We have MS SQL Server, integration services, .NET, actual business stuff is .NET. A big part of it is the backend. We pipe it through SSIS2 and SSAS Cube. Too much data to put into the front. I'm going to be burning through slides just so you guys know. Okay, so the requirement, it needs to be Excel-like. Data scientists use this, and anything but Excel makes them nervous and panic. So the way it works is you have a model. On this model, you define measures. On the measures, you define a formula which actually defines the structure of the measure. These measures, the final output is MPX that gets sent to an OLAP Cube. There's a beauty little diagram. The execution is deferred. So when they create the model, they write up the measures, they define the model, and then they publish. What this publish does is it will create a series of SSIS packages. The SSIS packages are basically put on a server, and there will be scheduling that executes them at a later date. There's too much data to actually execute, load up into memory or anything like that, so we just defer it, we push it back. So everything needs to be able to be defined as a package and kind of a pipeline. An OLAP Cube. So the head of this is something called an OLAP Cube. It's a form of data warehousing. So instead of a database where you just have your rows, you kind of store them at something called aggregate level. The way to think about this is a concept of dimensions versus facts. So a fact is like, it's a bit of information measured against something. A dimension is what that's measured against. So a fact will be 7, the dimension will be a date, color, and all that. So that's kind of that idea. Most of the stuff is not going to be that covered in this. There's a whole big solution. This is just a part of it. MDX is the expression language, multidimensional expressions. It's like a querying language for OLAP cubes. You define the aggregate at which you receive the data. It's like SQL, but you kind of specify the axes, and there's a bit more to it. But it's very important because how the client and external forces are going to interact with this is through this MDX. That is what cubes look like in production. That's what they look like in documentation. That's what they look like in production. So the biggest thorn is the query function. So the most important part of this is this language needed something called the query function. What it does is it captures a block of data that is defined earlier in this production, in the solution. The dimensions are defined earlier. That's also, we don't really worry about it. We just need to capture the fact, the fact row, the column row, what is in that fact table. And it effectively creates a measure, sends it to the OLAP cube. So the big takeaway of a query function captures data, puts it in the pipe gets sent to the cube. This executes on a publish. So when you click the publish button, that's when that executes. The MDX is what will execute on the cube. So here's the problem. The output is a cube. It belongs to Microsoft, not Microsoft, the client really, but the technology is Microsoft, it's no longer in our hands. So whoever works on the cube, whoever executes it, the way they're seeing this cube, we don't have a layer there. We don't have any kind of control over that interaction. The output, the actual output of the data in the cube is defined by this formula editor, which is our side. And there are different steps of execution. So the steps of execution is the first one, when they're typing this thing in. You need to validate, and when they're typing it in, the formula needs to understand what's happening around it in the model. The second part is in SQL. Now, this also specifies what data is being sent to the cube. The third part is the MDX, how that data is presented to the customer. Now, you can't perform any grandiose operations on it at any other level but the cube, because the cube, the operation has to happen at the aggregate. So it needs to, it's just how, the shape in which the data looks. It's, we need it to be changed at the last possible step with 90% of these. It's the 10% that's the problem. So we had an initial solution. It was just a simple formula. It just mapped straight to MDX. So it was a formula mapped to MDX, and it was like almost a listener that would crawl through the expressions and wait until a query is captured. Now, the first example, it worked. It's what would happen is you'd capture a query, it would write it to a property on the measure. So it knew that that measure would have to be populated by that bit of data, and then add one. That add one was done to the cube. So every single time you pulled the measure, it had the original data, it would pull it up, and then just add one to it afterwards, at the last step. Now this was done in MDX, so it was done at the cube, after everything, but how we built it is how it would output it. Second one, this is pseudocode. This is just like very rudimentary. So here's another example. Now let's say if a measure on the year 2011, the value is 5. Display data for column 1, or display data for column 2. Now, this is where the problem lies, because this previous and simple solution, the condition, the first expression, is evaluated at MDX. So if they pull this data at a year level, that will execute on year 2011. If they pull it at a decade level, it'll execute never, because there will never be year 2011, because you're only looking at decades. So it'll never ever execute. The actual solution is non-deterministic. You'll never really know what is happening, what you'll actually get between column 1 and column 2. So we are going to have a little working problem. Bob is a data scientist. He wants to write a model for this company. Now they want to capture their gross profit with this model. Now there's a problem, like with all data sets, there's omitted information. For some reason, the year 1993, there is no cost of sales or sales data. Another problem, this company is clandestine. They don't pay VAT. So they want to include VAT into their actual profits. So through violence and coercion, Bob found that he could actually get the gross profit of the company for 1993, but he'd still have to apply the formula to the sales and cost of sales. So this is what his formula looks like. This is what he now makes the formula, his problem. He wants to be able to use this. If the current year is 1993, I'll put another measure called gross profit. Or else, pull the sales through, multiply by 1.15, pull the cost of sales through, deduct it from that output. Okay. So we're going to actually start looking at the actual solution. The first step is the Lexer. When you're writing a language, you lex. What the Lexer does is it takes a nice stream of strings and outputs tokens. So you don't, when you start applying parse rules, you no longer deal with strings, you deal with tokens. Much easier, because once everything's tokenized, you don't have to deal with stuff like ambiguity. So if you have a string with a plus in it, you don't want the parser to detect that there's an operation inside of a string. What the parser will do is it'll take the string, just say string token, you don't have to worry about what's actually in it anymore. No more having to worry about white space. It's awesome. So the tool I used was called ANDLR, another tool for language recognition. Judging by some context clues, you can tell there are others, but this was the one I picked. The way ANDLR works is you have something called a grammar. Grammar is a big syntax document that you write up. You define your rules with it. It actually generates code. It actually generates a parser and a Lexer for you in the language that is in the language that you choose, really. It's so it doesn't have to, nothing really has to be invoked. There's no complex runtime or anything like that. There's like a listener that crawls through it. It's open source. It's written in Java. It's a nice little .jar, which is awesome. It's nice and simple. It supports Java, JavaScript, C#, Go, Python, C++, Swift. We use C# because the whole project is C#. So we have our Lexer. What does it do? It outputs tokens. It doesn't really care. Once you have the token, you don't have to care about what's in the token anymore. These rules are simplistic. They're effectively like, have any of you guys ever done a theory of computation in university? That regex with the automata. Simple. You have a character set, complement, clean equations. Okay. Think of it as like a regex with none of the features. It's awesome. So this is how they look. Okay. So here's just some examples of things that we needed in the language. So you had a member. Member is something between two block brackets. As you can see there, so the way it looks is you have block bracket. So the star is a clean closure, it means any or none. The plus is like another clean closure, but it means at least one or any. So what I'm saying is anything that's not a block bracket, closed block bracket. They want it to be very permissive with what they could put in there, sort of like anything. Strings, quote, anything that's not a quote inside of it. It's any or none because you can't just have two quotes as an empty string. The ID is a little bit more complex, so you'll have A to Z or 1 to 9, 1. A to Z, 1 to 9, or underscore. What this means is anything that doesn't really start with an underscore. Underscore are used for reserves. Underscore is something that's called commands. They communicate directly to C#. A discrete value is just amount of digits. There's also continuous, but it's just for simplicity, just a truncated version. But this is how it is. So you have 1 plus hello minus x. Discrete operator string, operator ID. That's what you really do. Here's just a little bigger example. So here's Bob's little solution. So we move through it to Lex. This is what you get. You get member. So the whole thing comes to member. ID. ID is generic. It's a name. It's a variable. It's the start of a function name. It's whatever. So you move through it. And then we Lex it. And it's at this point, no more having to worry about white space. You'll notice that I capture the brackets. So what that means is they're an implicit Lex token. So what they do is you use them to define rules, but you don't actually capture them in your expression tree, because I'm not going to know what to do with commas and brackets once the language has been passed. Then what we do with the tokens is we have the parser. The parser is rules that actually define the expressions, the core of this. What it does is you pass to the parser a token stream. See, unlike Lex tokens are, you can only just have one Lex token. You can't have a Lex token in a Lex token. One, the highest priority just becomes it. Takes over the whole thing. Expressions are the opposite. Everything's very nested and recursive. Fine. Inside of itself. You define them in the priority, so how it finds the expressions is the order in which you define them. So here's how the parser rule looks. You have expression. Some got left recursive, and find it on the left, use it on the right. So you have all of these are expressions, and two of those contain expressions. Effectively, just what you want to think. So an operator can have an operator in it. So 1 plus 1 is an expression operation. 1 plus 1 plus 1 is an expression, two expression operations, but one's actually in the other. What this really means is, let's look at 1 plus hello minus x. Whole expression is 1 plus hello minus x. But what's the actual captured information? It's the plus. Why? You may think it's not the minus. Well, because these are all ambiguous, it still moves from left to right across it, and it's going to prioritize the plus. Why is the minus included? Because it's actually part of the expression, but at a different point in the tree. So what's the next expression? Is 1. Next expression is now the minus, so it's hello minus x. Next expression is hello, and then x. So we have our list of how these are read. So now that we understand that, we have something called a listener. Now the listener is what takes all this information and actually works with it, starts to deal with it. Now this can get really, really, really complicated unless you make it not complicated. So we're going to make it not complicated. So we're going to have two rules. On enter expression, add child, set current node to child. On exit expression, set current node to parent. So let's go back to our expressions. So we have our expression. On enter, we set current, there isn't a parent, so we create a node. Captured information is plus. We step down, we set current to, we add child, set current to child. Now we exit that, so we set current to parent. And you move through it. All the way through, applying the same rules, and then you exit, you exit, you exit. When there's nothing there, you pass the expression and you have a tree. So now we take this and we apply it to Bob's formula, and this is what it's going to actually look like. This is the initial token tree. So what it has is a little bit of token information, the start of the token, the end of it. This is really for like syntax highlighting and stuff, which is very cool. But here's what Bob's going to end up. So trees. I just want to emphasize this. When I say tree, you need to think fractally. Every tree is in a tree, on a tree, amongst trees. Anything that interacts with a tree needs to act like a tree. Now it might sound ridiculous, but it's cool, because all that you get ever is one node. And then you say, you execute. And then that tree knows to execute its children, they execute their children, they execute their children, and moves all the way up. Okay, I just want to contextualize execute children. Noise, people. Okay. Most important part of the slide is that there's a lot of default animations, there's a lot of red, and I just wanted to give you something to remind you that you're still alive. The constructs. Now we have this tree, this little parse tree. What does it mean? What are these things? You know, you have a key value, you have an actual Lex token, and you say it's a part of this rule. It means nothing yet, so we're going to add some constructs. So here are some of them. Expression, function, operator, constant. It's actually just a function without a bracket. You still have to declare them with brackets because laziness and production timelines. A type declaration, a parameter, assignment, and a command. So here's some examples. Quick little thing, so we had a demo and I forgot to add Boolean literals. So that's what constant Booleans actually look like. So true, evaluates 1 equals 1 every single time it executes. So yeah, command. So command is a little low level, so commands just, you'll see them, it's not much to them, they just execute in C#. So the anatomy of the declaration, you have the signature, which is just the ID, or the ID and the parameters. This allows overloading. The type, which is the output. This is the syntax. I love Rust, so I stole the syntax and then just wrote that way. If you can't write in a language you love, write the language you love. That's a parameter, which has a thing, and then an expression, which returns. So all these constructs are kind of just wrappers around expressions. There's just another little view, the signature, the return, and the expression. Just want to emphasize, it's also a tree. So everything's around a tree. Everything's trees. Okay. So now we're back to our listener. So we're going to make it complicated? No, we're just going to add 3 more rules. On enter declaration, pop a declaration on the stack. On enter type, write that type to the item at the top of the stack. On enter parameter, write that parameter to the item at the top of the stack. On exit declaration, pop it off the stack, write it to scope. So, we enter our function, we pop it on top of the stack, we enter a signature. Now I'm not saying I'm entering this function signature, I just enter a signature. But I know, if you structure this properly, that it'll just work. So I enter a parameter, write it to the item at the top of the stack, type, write it to the top of the stack. Now we enter another declaration, it's an assignment. Pop it on top of the stack, you notice function isn't finished parsing, but that we don't care. Signature, return type, expression, pop it off the stack and write it to scope. Another expression, pop it off the stack, write it to scope. Another expression, pop it off the stack, write it to scope. Now the expression is a special kind of construct. It's more of just an initial thing. So the highest level expression is what is returned to the user. So that's ultimately what's executed. What that just does, it's an encapsulation of it. It's just to keep it along the same set of rules, so we don't have to have multiple listens. What we have here is Bob's tree, but now we have more information. Because we're trying to work through this, but we're still not finished, we're far from it. So we have if statement, current year, minus, query, multiplication. That actually means something now, but we still don't know what to do with it. But we still need type information. So type theory is a subset of category theory. I recommend you should read it up, and then you can explain it to me. The gist of it is every operation is a parallel operation of types. These determine what can execute, and the values are what actually execute. So just think of parallel trees now. So every time there's an operation that performs, there's an operation of types. And when 2 values become a value, the other 2 become a type. So the types. This is the kind of the core of it. This is how it works. So we have the different points of execution now that I mentioned. A type needs to, so you have a value. Now, it's still an abstract concept what a value is because it can mean lots of different things. But this is where we actually contextualize it. So, what the type says is how does this value behave when it's a node? And that means when it's in this formula, how does it behave? How does it behave if it hits C#? How does it behave if it hits MBX? And how does it behave if it hits SQL? Now, all of these need to happen because any one of these nodes could float all the way through and hit any of these points. And they'll need to know what to do. Another one is the coercion tree. So that's how the types interact with each other. How do they understand each other when they meet? Just as a definition, object. So now when I say objects, it's simultaneously MBX, SQL, and expression, and C#. It's going to be represented by a tree, but it's effectively all of these things. Okay, so types. We have 3 types of types. Naming is hard. So we have primitive, complex, and iterator. These are the ones I use. These aren't all kinds of types, but yeah. So primitive is a single value. It ignores its kids. It doesn't care about them. It just emits a single value. They're atomic is the terminology people use. So it'll be the end of the execution. So all the way down, it'll be the last point. It doesn't execute its kids. The big definition and understanding that you need to know is that it is a value. Complex types have values. So what these do is they have effectively properties. The way the properties have been defined is it's a signature and an index with a getter and setter mapped to them. It's not really that much to all of it, but effectively what it does is you see the parallel trees, the actual definition on the right, left, and the actual values. So in the actual language, you would find the properties by name, but whenever they're used afterwards, they're actually mapped by index. Iterator type is I needed collections. So what an iterator type is, it's actually just a function that executes on each of its children. So you define on execute child, and you redefine it. On execute child, do something, and then it invokes that, and you'll have an n amount of children, and we'll hit each one. Okay, so worked example. We have. I don't plan for that. Okay, so we have our parallel tree. The green ones are types that we understand. So parenture, because these have all been defined, you'll understand the type. So MDX effect type really means it needs to hit the cube. It'll only ever be understood on the cube. There's no local understanding of it. The gray ones are types that are not determined. So we have 3 that are functions, but the type is determined on what's going to behave in them, how it's going to act. And gross profit, we don't even know what that is yet because it's a variable. So we're going to talk about context. What is happening around the function, the formula? So what it does is you have the current measure. So you write a formula on a current measure, it needs to look out and around at all the other measures around it. Pulls in all the model information and creates a glorious memory leak. But anyway, it needs to understand its environment. It's effectively what we really mean. So what a scope is, what we've done is create scope. Scope is 2 parallel hash tables. One is a hash table of values, and the other one is a hash table of scopes. So every time you step into a value, you step into a scope. So like hacky crap, like the way the complex functions work is their children are just set into its local scope. So you say, I evaluate this value, you step into its scope, and then you just evaluate the local variables in that scope. It looks like such. So you very effectively have a name to a tree. So what do we get from this? We get gross profit is now a measure. Anticlimactic, but it's more information. Unrolling. Now, because we write this in the model view, which is the very Excel-like grid. Now, when it's done, when everyone's happy with it, they click publish and it publishes. Problem is that publish is we lose information on what's happening in the model because it happens far away. Now, the problem is why we can't do it in the model is because we need information provided by the publish. The tables and the SQL stuff is all defined in the backend. So we need information from both. So the way this works is a step called unrolling, where we build it into one big expression. So it's 3 functions really. So it allows the declarations and those constructs to execute. Now when I mean execute, I mean unroll. So they basically, I don't know how to describe it. The expression kind of unrolls itself onto that node using the values there. It gets all the values for the variables and it assigns the actual types. Because at this point, types have just been a name, concept. But this assigns the actual signature. So we have unrolling literals, very easy. So literals are, there's 3 types of literals. There's the continuous, which is like an integer. Continuous, which is like a real, a discrete, which is like an integer, a string, which is like a string. And a Boolean, which does not exist and never will. So it looks like that. What you're really doing is you're finding it's a type and you're mapping it. So references. So what reference does is reference, like a variable. So you just type X. What it does is it looks at its current scope for a tree, takes that tree and unrolls it onto the orange. That's what I mean by unrolling. I need you to picture it in your mind. It unrolls that node onto it and ultimately replaces the value. The way functions and constants work is you take the values that have been passed. So you see the 1 plus 2, that's what you're going to get. And at the top, you're going to get the definition. You take those 2 values, you map them to their corresponding parameters. You get the names from the one, the values from the other, and you create a little scope. And you take the expression from from the declaration, and you unroll it in that scope. And because of the previous step, it'll unroll the values as they were variables, but you just created this fake context in which to unroll them. And you'll end up with that underscore add, which is a command. It just communicates, so if this needed to execute locally, it'll execute like that. The type coercion. So we have a type tree. It looks like inheritance, but it's not. So what happens is I was studying discrete maths at the time, so it's very exciting for me. Each type coerces to a parent. Every time you define a type, you've got to define a parent that it can coerce to and how it can coerce. So what you define is a partial order relation, which is a form of it's a form of relation, but that's like transitive, antisymmetric, blah blah. What it really means is any two types, you can find a lowest common ancestor which they can meet. So there will always be a parent for any two types. So anything can interact with anything, no matter how high it is. So if you have like measure, real, int string, they can meet an entity. Now entity, I'll chat about it later. It's how I get to the meat of the specific stuff that we need to do. This is still a bit general. But yeah, what you just need to remember, MDX is the top of the tree, but everything still meets an entity. So entity just allows there to be another step. That's what will really be passed through to SQL. So here are some functions. So we have current year returns MDX, which means that it needs to be passed to the cube. Minus is MDX. Why is minus MDX a multiply entity? Because cube is aggregate data, SQL is detailed data. Multiply is a linear operation. So 1x or 2x plus 2y plus 2z is the same as 2 in brackets x plus y plus z. Minus not the same. Minus, what's it? X minus 1, y minus 1, z minus 1 does not equal x plus y plus z minus 1. It's not the same. That's the best way to think, that's the way to think about it. So the multiplication can be passed to the cube and will behave the same at any aggregate level. So we're going to find our types now. So if, what is your type? Because I don't know, ask my kids. One of his kids is minus, so he says, what's your type? I don't know, ask my kids. Multiplication, what's your type? Ask my kids. Hi, his kids have a type. It's a measure and a real, but if you have a look at the multiplication that is defined, the output is entity. So measure and real both meet an entity, so that can be used. So boom, it's entity. So minus, you have now an entity and a measure. What happens here? Its type is MDX, so it's MDX. Now if statement, there will be multiple, so I've just given two for example. If the condition is a Boolean, it means it's locally executed, the decision can be made before it goes to the cube, but the condition is MDX, which means the decision is made in the cube. So everything has to be MDX. So we'll pass that order. Okay, so we unroll. So let's have a look. If statement, these are kind of pseudo, but if statement looks like that. Current year. So current year is actually just wrapping a getDate function, getDate command, a year command, and an equality. So what I'm saying is get the date, get the year of that date, and is it equal to X? So what it's going to look like is, yeah, okay. One other thing, sorry. The IM is an internal measure command. So that data. But IM means that you need to capture an internal measure. So when we unroll, this is how it's going to look. So we break up this whole tree, we take all those little functions and we replace them with their full trees, and you get this. This is the final execution. So execution. Don't Google image execution. So we have a big tree now. All the information that was ever needed at the beginning of the model is handled by that scope and that unrolling step. It's now been put in the tree. It's actually stored till later use. They're happy with the model. They click publish. It goes on with its merry day. The problem with this means there's no recursion. You can't, because nodes will infinitely unroll and you die. Yeah, stored in database. Now the execution is quite simple. It's that simple rule. If you execute your kids first. Okay, so this is now where we get specific to it, entities. It's not the best name for anything, but if I called it thing, my tag tree wouldn't allow pull request. So what this is, there's two concurrent trees. So you have the MDX tree and the SQL tree. These are just how they're built, and when a type coerces to an entity, what it does is it emits a no. So it means that something has to behave in MDX or SQL. And that's how it's actually captured in this entity tree. So in the coercion step, it emits another tree. They come onto the side like that, I guess. And it defers the execution. So what the SQL tree does is it builds the SQL, I guess. So we have a series of SQL imports that passes it to the queue. Now, what we have is a detail level. Detail level means just rows. Just think rows, like in a SQL table. It's patchy. The dimensions aren't guaranteed. It's whatever information you have, but it's at the lowest possible granularity, the lowest dimensional combination. It will capture these internal measures now. So when that little IM emits an internal measure, the communication thing, it's a node that's passed to SQL, will be what's captured by this tree and basically generates an internal measure. It generates like an ID. And then what that ID does is it's captured as an internal measure. So what an internal measure is, it's like, think of a block of data that needs to be sent through. But what it really is it's an ID saying, there is a block of data. So SQL passes through the block of data, the internal measure, it communicates the block of data, and it allows the MDX to piece these things together now. So the MDX is that last step, but we don't ever actually execute the MDX, we just build it, we talk power to it. And we write it on top of something called the calculated measure. So in the cube, we have a bunch of internal measures, these are not seen by the client. On top of it, we have calculated measures. So calculated measures are built by the formula at the end. So now after all the data is done, there will be MDX that will be captured through the emitting of the entity node. It's effective, and the way it's designed to work now is it stitches these things together. So if we go back to the earlier example where there was a condition and two query functions. What will happen is it'll actually both will be sent through. And then the MDX, because it's executed whenever someone queries the queue, it'll know which one to return. Now, if there was a condition there that could be locally executed, it'll just pass through the one. So here we have how the execution is actually going to go. So we start at the top because that's the information, that's all the information you actually get. So now these underscores are all commands actually locally execute. So we say new if executes. There's no kid's got to execute. They say no kid's got to execute. They pass it down to, we get to these little points here. Now, these can execute because they actually have value. At the bottom of it, get date doesn't have anything to evaluate. IM, the only thing it has to evaluate is the literal, the information's there. So it executes and they collapse on each other. The get date turns to date.current, which is an MDX expression because it's pure MDX. There's no information that needs to happen locally. But the IM collapses to an I1, so it collapses to an ID. But on the little console there, you said that it just keeps track. That I1 has been captured, and in the SQL you can see we're now putting through sales as underscore I1. Now we evaluate these. You have the multiplication. The multiplication is linear. So collapses. Year just collapses to year function. There already is one similar to it, but it passes each child in as a child. So the mapping is 1-to-1 there. That's pure MDX. The I1 doesn't change the MDX because it actually changes in the SQL. As you can see now, the SQL has applied the linear operation, and the cost of sales is passed through, so that's the underscore I2. So all the information is there that it needs. Now in the SQL, it knows to import these. And in the actual MDX, you can see it's starting to be built. It knows to refer to them as underscore I1 and underscore I2. So when we collapse these two now, so these are pure MDX expressions, the minus becomes I1 minus I2. So it now refers to these. It knows how to deal with them in MDX because it passed the appropriate data through. We're not changing the SQL anymore because now we've had a territory that is just MDX. It knows to refer to the measures.gross profit because on the gross profit object, we just said this is what is being sent to as MDX. And then if statement follows, we get this. And yeah, so Bob now has a SQL and an MDX query. So what will happen now is that SQL query will be passed through to SSIS. It'll be passed all the way through to the queue. That MDX expression will be built into a MDX expression calculated measure on top of it. He'll take it to the bank. They'll celebrate. They'll throw so much money at him, he bleeds. And there'll be food, wine, much rejoicing. In conclusion, that worked. It's like two guys that use it, but that's cool. Yeah.